In the last module, we looked at critical radius of insulation, and we did a small problem where you could see the effect of the critical radius on the heat transfer. So, if you are below or above the critical radius, how the heat transfer is going to vary. Just continue with the 1D conduction further. This is a slide which is there, which is going to give you the whole view of whatever we have done today. Okay, one dimensional heat conduction equation without heat generation, plane wall, cylinder, sphere, temperature distribution, heat flux distribution, heat transfer rate, thermal resistances due to conduction. Okay. So, next is 1D heat conduction steady state with volumetric heat generation. So, if you have uniform volumetric heat generation either by a chemical reaction or electrical heating or whatever. So, if that is a known quantity, so E dot G is I squared R per unit volume. So, you divide by the volume of the element, you will get Q dot, which is the volumetric heat generation rate. If that is known, your linear temperature distribution that you would see in a plane wall will now no longer be linear, because that material itself is generating heat. So, temperature distribution therefore would get altered. That is what we are going to see now, how temperature distribution is altered for case with uniform volumetric heat generation both in plane as well as radial system, plane wall as well as radial system. So, this is essentially your 1D conduction equation, 3D conduction equation with volumetric heat generation, and if you have steady state, the rho Cp dt by dt goes away, 1D in x. So, these two terms go away. We are now retaining the volumetric heat generation rate, which is Q dot by K. So, if I want to solve for this, it's instead of 0 here, I have a Q dot by K, that is the only thing. So, ideally we should have solved for this first and set Q dot equal to 0, you would have got whatever we got there. So, but anyway, does not matter. We are looking at a case where this is a plane wall, and for a plane wall as shown here, this is a plane wall. This is this geometry is taken out of convenience. What do I mean by that? The line of symmetry, the center of the plane wall of thickness 2L is where the origin is supposed to be. What is wrong if I take the coordinate system at the left wall? Nothing is wrong. Okay, it is just that your equation for the heat conduction, temperature distribution would look a little nastier, and some physical insights which you would get otherwise may be hard to get from the solution. That is the only reason why symmetry or the center line is taken as the origin. For example, this is asymmetrical boundary condition. By that I mean, I have T infinity 1 and H 1 very different from T infinity 2 and H 2. So, this could be a glass of a window of an oven, where inside is H 1 T infinity 1, which is much different from outside, which is H 2 T infinity 2. So, temperature distribution there, of course, this is a heat generation thing. So, if you look at in fact, a common example of this would be your rear on the car on the back side you would have these rear view mirror. You will have the glass through which there will be electrical wires which would be there in cold countries, so that when snow or ice falls on the back, the heat from the wires would melt, so that you would have a clear view of traffic behind on your rear view mirror. So, your rear view mirror sees through the glass on the back side of the car, but if that is full of snow and ice, you will have a problem. So, it is like that, where you have a heat generation in the glass. Inside is your ambient car passenger comfort condition, 25 degrees, 22 degrees, outside may be -5 or -10. So, this is one such situation. Of course, a classic case would be a simplified case where H 1 H 2 are equal, T infinity 1 equal to T infinity 2, and that would be a symmetric profile. Anyway, so we will take a look at this now. I am just going to set up the equation for you. The solution is here for us to do. So, 1d, so d square t by dx square plus q dot by k equal to 0, that is my governing equation. So, d square t by dx square equal to minus q dot by k. If I integrate once, I get dt by dx is equal to minus q dot by k x plus c1. Integrate again, t of x is equal to minus q dot by k x squared by 2 plus c1 x plus c2 is equal to minus q by 2 k x squared plus c1 x plus c2. This is, as you can see, function of x squared. So, we would expect it to be a parabolic relationship. Now, we go to the boundary conditions. So, I have, this is my center, this is my wall, minus L plus L h comma t infinity 1 h t infinity. Let me just go to what has been done in the slides. 1 and 2 are reversed. Okay. So, this is 1, 1, 2, 2. Okay. So, I can substitute for this. Now, point to note here, this is convection, the heat transfer is, this is Q. Okay. Unlike plane wall where heat would go this way, here what is hotter? The material is hot, surroundings are cooler. So, I would have Q going out this way as well as this way, because the center temperature is going to get hotter. So, the higher the temperature in the center, the greater is the difference between the center and the boundary. So, here I have to say minus k dt by dx at x is equal to L is equal is h times T of L minus T infinity 2. This is one of the boundary conditions. The other boundary condition will also be a derivative boundary condition. I hope you are able to understand here. Dt by dx has C1, T has C2, but both my bound, suppose I had, okay, suppose I had a fixed temperature. So, this is Ts2, not a problem. T at plus L is Ts2. So, Ts2 is equal to minus q dot by k L squared by 2 plus C1 L plus C2. I have used the condition where C1 and C2 both are coming into the picture. Then I can use convection on this side to get C1 first, and from there after that get C2. But now if I have both of them to be convective boundary condition, which means both are derivative boundary conditions in temperature, dt by dx, I am not able to get C2 at all in my relationship and be able to solve for it. So, what do I do? Well, it's then you have to basically take a look at the overall energy balance. So, q dot, which is coming into V, is basically energy out. So, E dot in minus E dot out plus E dot generated is equal to 0, because steady state nothing is coming in, E dot generated is Q dot into V, E dot out is based on these two. So, E dot out is equal to this. From this you would get whatever you need for the other boundary condition to get C1 and C2. We will see what it is. Okay, so, here you have, of course, this is a simplified case where surface temperatures are given Ts1 and Ts2. I told a more complicated case. This is straightforward the way we had done for no heat generation. So, you have two unknowns, put it in the temperature equation C1x, C2x, I mean C2. So, you would have two equations, two unknowns, solve for C1 and C2, you would get the result, substitute back, you would get the temperature distribution. That is what is shown here, where the temperatures are specified as Ts1 and Ts2, and Ts1 was greater than Ts2. So, you get a parabolic relationship, a linear term here, and a constant term here. Now, when Ts1 equal to Ts2 symmetry boundary condition, the middle term will vanish and you would have average of the two equal ones. So, either Ts1 or Ts2 will be there and this one would remain as it is. You would get a parabola with temperature being anchored as Ts on both the walls. That is a beautiful thing for symmetry boundary condition that is shown here. Maximum or center line temperature will be when x is equal to 0. You substitute here, you get Ts plus q dot L squared by 2k. So, this is a very simple exercise, I do not want to spend time on this. Point what we need to know is when I have a derivative boundary condition, that is one of them is a convective one and other is a surface temperature, that also can be solved. But if both are surface temperature boundary conditions like this and Ts was not known to me, okay, here Ts1, Ts2 are known. So, I am putting in numbers there. Suppose this were not known and only H and T infinity was known symmetry wise, then I will say symmetry wise if both are known, then I am going to say the following. Let me just go back. So, E dot out, let me say H1 equal to H2 T infinity 2. If H1 is equal to H2 and T infinity 1 equal to T infinity 2, E dot out would be H into surface area into Ts minus T infinity, right. Is this correct? Not fully. Why? Because this is one surface. I need two surfaces, heat transfer what is going this way as well as this way. So, E dot out would be 2 into H, both sides H is the same, surface area into T of L minus T infinity. It could be T of minus L or T of L, does not matter, because when the boundary conditions are symmetric, when boundary conditions are symmetric, temperature profile or temperature distribution will be symmetric. So, from here this is Q dot V, this is a number. From here I will, these are all numbers. So, I would get T of L which is a number. This T of L I will substitute here, T of x is equal to minus q dot x squared by 2 k plus C1 x plus C2. Put that in here, I would get a number C1 and C2. So, I would get expression for C1 and C2. Expression in C1 and C2. Other would be the derivative boundary condition at you have symmetry boundary condition or whatever dt by dx is equal to 0 at the center line, which would make C1 equal to 0 and therefore, C1 goes to 0, you will get C2. So, symmetry dt by dx equal to 0, therefore, C1 will become equal to 0. And then because C1 equal to 0, you have an expression where C2 is the only unknown, you will get C2 and from here you will get temperature distribution is minus q x into 2 plus C2. Okay. Even when you have a convective boundary condition, you can, without putting in numbers, you can make this a nasty looking thing by saying Q dot V is Q dot into surface area into 2L, that is the volume. Volume is E dot generated is Q dot into V is Q dot into 2L into surface area. So, that is also there, put that in here, which is 2 HAS T of L minus T infinity. The AS will get cancelled, 2 will get cancelled. So, I would get T of L is equal to Q dot L divided by H plus T infinity. this you can use right here and get the C2. Okay, multiple ways of doing. I have shown you the philosophy of how this is done. Okay. Okay. So, symmetric case we have seen, and this is how the graph temperature distribution would look. The center line is the line of symmetry, dt by dx equal to 0 at x is equal to 0, which is like an adiabatic boundary condition or adiabatic surface at mid plane, which is what we are trying to tell you. There is no heat transfer across the symmetry plane and may be represented by an adiabatic surface. Okay. Okay. That is whatever I have covered is written here. Common situation where the temperature of the adjoining fluid is known and Ts is not known. We have looked at how it needs to be done. Okay. Okay. Now, we have this one, and this whole thing has been done for you with a symmetry boundary condition. Okay, symmetry boundary condition. Okay. 1D heat conduction in radial system, which is a cylinder with heat generation. Our governing equation 1 by r d by dr of r dt by dr, k comes out plus q dot by k equal to 0. Go through the maths, you will get a temperature distribution. Here now we are looking at a current carrying conductor or an electrical wire. So, it is a solid wire unlike the hollow cylinder that we saw. Okay. So, again here uniform volumetric heat generation will give me the center line to have the maximum temperature. So, this is a very useful common geometry right from current carrying conductor to a nuclear fuel rod. The fuel rod is generating heat, and the heat transfer is basically 1D radial conduction in a cylinder. Okay. So, q dot, and this q is going to come out this way. Just as a plane wall, this is now a cylindrical geometry. That is all is the difference. This is my z coordinate, z is L is about 3.5 meters, radius is of the order 12 millimeter, diameter is of the order 12 millimeter. So, radius is of the order 6 millimeter. dt by dr is much larger than dt by dz. So, 1D radial is a very good assumption even in a complicated system like a nuclear reactor. So, this is the fuel bundle I am talking about, nuclear fuel rod, and here typically you have H comma T infinity. Surrounding is convective boundary condition. The constraint is the maximum temperature T max should be lower than T melting point of that material always. Otherwise, the fuel rod would melt and there will be a problem. So, what should be the H comma T infinity conditions and the volumetric heat generation rate such that the temperature never reaches or exceeds the melting point. That is the whole idea. So, we have a temperature distribution, and if you look at the symmetry boundary condition at the center, dt by dr equal to 0 gives me C1 equal to 0, go back into T, get C2, and you get the temperature distribution as a function of radius. Q dot r naught squared by 4k, which is a constant, times 1 minus r squared by r naught squared, parabolic in r. This is a constant, this is a constant, 1 minus k into 1 minus a into r squared form. Ts, maximum temperature is at the center line, from here itself we know that, and so when you put r equal to 0, this term will vanish. Maximum temperature is surface temperature plus q dot r naught squared by 4k. Okay. So, all that is given here, and you want to write it in a non-dimensional form. So, local temperature minus surface temperature divided by the center line temperature minus surface temperature is nothing but 1 minus r squared by r naught squared. It just comes by using these two and dividing one by the other. T is a local temperature distribution, T naught is the maximum, subtract Ts from both sides and divide the top by the bottom equation, you will get this. So, non-dimensional delta T, local delta T, what is this delta T? Surface minus any inner location divided by surface minus center location, which is the maximum, is 1 minus R local divided by R naught squared. Obviously, this right hand side is less than 1 because left hand side also is less than 1, and again as we did for the plane wall, E dot generated is E dot out, volumetric heat generation Q dot into volume pi R naught squared L is equal to H into 2 pi R naught L into T surface minus T infinity. So, I get T surface from here, and based on all this we have a simple numerical problem where we are going to use the concept of volumetric heat generation, resistances in series, everything. Okay. So, I will go through this quickly, about 5 minutes, is all solved here very nicely for you to take a look. So, we have a plain composite wall made of two materials A and B, uniform volumetric heat generation rate is there on this left hand side, Ka La is known, B has no volumetric heat generation and thickness is so and so. The inner surface of the wall material A is insulated, that means boundary condition at the inner wall is adiabatic, dt by dx equal to 0. Outer surface of material B is cooled by water stream giving you H comma T infinity. Sketch the temperature distribution that exists in the composite wall under steady state condition. Determine temperature T naught on the insulated surface, that means T naught at this left wall which is x equal to 0, and temperature T2 of the cooled surface which is the outside right hand side surface. It is a very standard problem, and in fact, when I go to this reactor also it is the same type of situation. You have a fuel rod, you have a cladding which is made of zirconium which is going to be non heat generating, no heat generation here. This is fuel rod has heat generation, that is where the uranium dioxide etc. is there. So, our problem is exactly like this, but for a plane wall. This part is heat generating, there is a part which is non heat generating, dt by dr equal to 0, there the left boundary is insulated. So, same type of problem. So, I will have typical assumptions. This is my schematic, two walls composite, left wall which is insulated. Okay, there is heat generation in this A material, nothing in B material. So, I would expect the B material should have a linear temperature profile. We have studied heat transfer in a plane wall without heat generation. So, linear. Here uniform heat generation, symmetry line of maximum, here temperature would be maximum because this all heat generated is going to the right hand side. So, for maximum temperature has to be at this x equal to 0 location. Parabolic, linear, and then convection on the outside, simple. That is how the answer should be, that is how the plot should be. Let us take a look. We have assumptions here, 1D steady state conduction, okay. Symmetry at x equal to 0, no variation in axial direction, we have thermal conductivities which are constant, negligible contact resistance, heat transfer coefficient is constant on the outside, and if at all there is radiation, it is taken care by the heat transfer coefficient value. And qualitatively, this is how my temperature profile, even without putting a single number, I will be able to say that in material 1 I would have a parabolic relationship, in material B I would have a linear relationship, and then this is just convection. Okay. So, x is equal to 0, x is equal to LA, LA plus LB, and further downwards. Okay. So, let us just go back. 0 slope at insulated boundary, that is what is indicated by dt by dx equal to 0. So, I will not have this going and joining at some angle, it has to be horizontal. The tangent to this temperature curve should be horizontal, dt by dx equal to 0, that is important. Okay. So, if you do a numerical solution of this, the boundary condition dt by dx equal to 0 should translate to a flat profile at this location, okay, flat at x equal to 0. Linear in material B, sorry, there is a typo here, it should be linear in material B. The temperature distribution in the water is characterized by large gradients near the surface, this is typically convection, and slope change is large at the interface, it is a ratio of the thermal conductivities, obviously, because heat coming in through material A is removed by material B. So, minus k dt by dx at A is minus k dt by dx at B. So, the gradients dt by dx at A divided by dt by dx at B would be Kb by Ka, or otherwise it is Ka by Kb in case of the other ratio. Okay. So, outer surface temperature is obtained by simple energy balance. I have Q, which is 1.5 into 10 to the power 6 watt per meter cube. What is the region of volume? This volume of material A. So, L A into surface area, which is into the plane of the paper. So, A s into L A is your Q, that is equal to H A s into delta T. The A s will cancel, so I will be left with Q dot into L A. I will work with heat fluxes here because this is a plane wall, all the areas are the same. Therefore, Q double prime is Q dot into L A, actually volumetric generation into total volume, but because all the areas will get cancelled, I can work with just the heat flux. Q dot into L A into surface area divided by surface area is what is heat flux, that is 1.5 into 10 to the power 6 into thickness 50 millimeter, that is 0.05 meter. Again in the diagram millimeter is missing, it is written as meter. So, please make a note of that. Watt per meter squared 75,000, that is equal to H into T2, this outer surface temperature minus T infinity. From this I will get this as 105 degrees centigrade. Okay. Then temperature at the mid plane. So, this is a parabolic temperature distribution, we know that. So, T naught is Q dot into L square by 2K plus T surface. So, this convective condition is there on the outer surface, but not there on the interface. Please remember, this is a sandwich wall. So, convection is on the outside, but not here. Okay. So, parabolic is still here. This is a temperature which we will have to find the interface temperature, from that this has to be found. But between in material B, it is single just conduction. So, K Q is equal to minus K into area into T at this location minus T surface divided by L, pure conduction problem. So, from that if I put, I would get this interface temperature, and from this I can do this substitution here. Other way of doing it is like how we did in the current carrying conductor problem in the cylindrical coordinates. You take the Q coming in, one conduction, another conduction, both are perfectly acceptable. So, I can go backward, I did convection here, go through conduction in material B and then go through material A, or stop at the interface here and do complete resistance analysis the way we did. Whichever way we do, we are going to get the same answer. T naught is 140 degrees centigrade. These are all very simple exercises, how resistances are calculated, etc. So, you get 140 degrees here. The interface temperature is 115 degrees centigrade. Please note, all the resistances are calculated per area basis because A is not known. You could take it as 1 and calculate, and then the subscript, I mean the superscript double prime will vanish. Okay. Okay. So, based on this, we have the plot now with the numbers. T naught is 140, T interface is 115, T2 is 105, and this plot as we had seen is just there. So, the resistance to heat transfer by convection is significantly larger than due to conduction in material B, and so you will see the large temperature drop. Okay. So, with this we will end single one dimensional heat conduction with volumetric heat generation in cylindrical as well as Cartesian coordinates. From next module on, Professor Prabhu will take over and he will talk about heat transfer through extended surfaces or fins, then go to transient conduction. Thank you.